So if you were to, I don't know, crack open the hood of a really cutting-edge modern AI model right now, just to figure out why it absolutely refuses to run locally on your phone, or your laptop even, you wouldn't actually find a processing issue. And it's not a battery issue either.
No, definitely not.
Right. You'd find this massive, just completely unyielding 34 gigabyte brick wall. It's this engineering nightmare that everyone calls the KV cache bottleneck. And right now, the industry's only real solution to get around that wall is to, well, literally give the AI a form of localized brain damage just to force it to fit.
Yeah, it's sort of the dirty secret of edge computing right now. I mean, we have these incredibly capable models, but the sheer physical memory required to hold their active memory, the actual context of the conversation you're having with them, it's just scaling completely out of control. We are hitting the absolute physical limits of consumer hardware.
Welcome to this deep dive into the source material. For anyone listening, whether you are, say, a machine learning engineer prepping for a high-stakes deployment strategy meeting, or maybe you're just a curious learner trying to understand the actual realistic future of AI on your everyday devices, the phrase KV cache bottleneck probably sounds like impending doom.
Oh, it represents a fundamental barrier. It is the primary reason your phone has to constantly ping a server farm hundreds of miles away just to, summarize a PDF or draft an email.
Exactly. So today, we're tearing into a stack of 4 highly interconnected, incredibly dense draft papers. They're from something called the Shannon-Prime project, and these are dated May 2026. And I have to tell you right out of the gate, these aren't your typical computer science papers.
Not at all.
Right. Like, they aren't just tweaking existing Python code or proposing another clever software heuristic to shave off a few megabytes. They're proposing a radical, purely mathematical geometric framework for transformer computation.
What's fascinating here is just the sheer audacity of the approach. I mean, the AI industry has spent years relying on lossy empirical tricks to shrink these models down. We've treated data compression as this messy afterthought.
Yeah, like a chore.
Right. You build the giant model and then you try to violently hack it down to size. But this research, it introduces a unifying algebraic principle where compression isn't an afterthought at all. It basically becomes a fundamental, provable property of the mathematical space that the model actually lives in.
Okay, let's unpack this with a visual, because it helps me. Imagine you have an incredibly overpacked suitcase,
Right.
right? And you're trying to force it into the overhead bin of an airplane. Traditional AI compression is essentially jumping up and down on that suitcase, violently smashing it shut, and maybe throwing out a few pairs of your socks when no one is looking, just to make it fit.
Hoping the zipper holds.
Exactly. You are inevitably breaking things inside. But imagine if you suddenly discovered that your suitcase was actually made of origami. And by its very geometric nature, if you just touch the right corner, it folds itself perfectly flat without breaking or removing a single item inside.
That is a phenomenal way to visualize what we are about to discuss. We're moving from violent, lossy compression, the jumping on the suitcase, to elegant, lossless geometry.
So our mission for this deep dive is to decode exactly how Shannon-Prime pulls this off. We're going to unpack how they use incredibly high-level abstract algebra, specifically something called complex multiplication on elliptic curves, to achieve provably exact compression and what they call calibration-free quantization.
Which is a huge claim.
Huge. And we'll translate the dense number theory into clear aha moments, showing how this could fundamentally rewrite the rules for how AI is deployed.
To really appreciate the elegance of their solution, I think we first need to quantify the sheer scale of the problem they're solving. So let's look at the systems paper from our stack. It outlines a very standard, modern deployment scenario. A 32-layer transformer model with a 4096 hidden dimension and a 32,000 token context length.
Which, just for context for the listener, is pretty much the gold standard for a good, robust local model today. If you want to feed an AI a whole financial report or a short book, that's your 32K context window.
Right. But if you calculate the physical memory required just to store the key and value states, the KV cache, which is essentially the model's short-term memory of the conversation, for that single sequence, it comes out to roughly 34 gigabytes of memory.
34 gib. Just for the we aren't even talking about the model weights themselves, right? Like the actual brain of the AI, just the temporary scratch pad.
Exactly. Just the scratch pad. And that completely crushes mobile neural processing units, or NPUs, and edge accelerators. Your typical high-end flagship smartphone right now might have, 8 to 12 gigabytes of total unified memory?
Yeah, if you're lucky.
And the operating system needs a significant chunk of that just to keep your phone running. So holding a 34 GB cache locally isn't just difficult, it is physically impossible.
So play devil's advocate for a second here. Obviously, people are running models on phones. We see local AI apps popping up everywhere. How is the industry currently getting around this 34 jibble of nightmare if it's physically impossible?
Well, they cheat. Or, I guess more politely, they use methods that throw away information. They use quantization-aware training, which shrinks the precision of the numbers, turning highly specific decimals into chunky integers.
So that damages the accuracy, right?
It does. It requires massive retraining to try and compensate for the damage. Or they use token eviction strategies, like streaming LLM.
Right, I've read about streaming LLM.
Yeah.
Doesn't that just literally forget older parts of the conversation to make room for new ones?
It absolutely does. It keeps the very first instructions and maybe the most recent few paragraphs and just throws everything in the middle into the void. Or they use low-rank factorizations, which try to approximate the massive data tables with smaller, just less accurate ones.
Yeah, so going back to our suitcase analogy, they really are throwing out your socks and hoping you don't notice. Or they're just smashing the suitcase and hoping the laptop inside still turns on when you get to your destination. It's fundamentally lossy.
Yeah.
Every trick we have right now degrades the intelligence of the model.
Yeah, they're all lossy heuristics, trial and error engineering, basically. But the Shannon-Prime solution completely abandons that brute force approach. Instead, they propose taking the entire forward pass of a transformer. So every single neural network layer, every matrix multiplication, every single calculation, and treating it as a sequence of endomorphisms on a single complex multiplication, or CM elliptic curve.
Okay.
And not just any curve, but specifically one over the imaginary quadratic field q root negative 163.
Okay, stop right there. Q root negative 163. I mean, that sounds genuinely terrifying. I feel like we just jumped from computer science straight into graduate level pure mathematics. Let's break that down for the listener. Why that specific, highly intimidating number?
It does sound intimidating, I know. And it really highlights this fascinating cultural clash between AI engineers who are used to hacking Python scripts and pure number theorists. The choice of negative 163 isn't random. It is purely functional. In number theory, negative 163 is what is known as the largest fundamental discriminant with a class number of exactly 1.
Okay.
These are known as the Heegner numbers.
Heegner numbers. Let's pause and define our terms here,
Yeah.
because we promised to translate the dense math. What exactly is a fundamental discriminant, and what does it mean to be an imaginary quadratic field? Assume I haven't taken a math class since, like Calculus 101.
Fair enough. Let's start with the field. A field in mathematics is basically a sandbox where you can add, subtract, multiply, and divide numbers, and you are guaranteed that the answer will also be inside that exact same sandbox.
So like fraction.
Yes, the rational numbers, fractions, are a field. Quadratic means our sandbox is built around squared numbers and square roots. And imaginary just means we are dipping into the square roots of negative numbers. So q root negative 163 is a very specific sandbox built out of fractions and the square root of negative 163.
Okay, I have my sandbox. Now, what is a fundamental discriminant?
Think back to middle school algebra, the quadratic formula. The part under the square root sign b squared minus 4x, that is the discriminant. It tells you the fundamental nature of the roots of the equation. So a fundamental discriminant of negative 163 means we are building our entire mathematical sandbox around a curve whose fundamental geometric nature is defined by that specific negative value.
Interesting. And are there a lot of these?
No, there are only 9 of these specific class number 1 Heegner numbers in existence. Negative 163 is the absolute largest one possible.
What does class number 1 actually mean for us practically? Like, why do we care if the class number is 1 or a million?
If we connect this to the bigger picture, having a class number of 1 makes the ring of integers for this field a unique factorization domain, or UFD.
A unique factorization domain. Okay, let's unpack that.
Think back to the fundamental theorem of arithmetic you learned in grade school. It states that every integer greater than 1 either is a prime number itself, or it can be uniquely factored into prime numbers.
Right.
The number 12 is exactly 2 times 2 times 3. There is absolutely no other combination of prime numbers that equals 12.
Right. It's unambiguous. 12 is always 2, 2, and 3.
Exactly. But when you move into higher dimensions and complex number fields like our imaginary quadratic sandbox, that simple rule often breaks down. In many complex fields, you can actually factor a number into primes in multiple completely different ways.
Wait, really?
Yeah, the math becomes ambiguous. The fundamental building blocks lose their unique identity.
That sounds like an absolute nightmare if you're trying to store precise data.
It is. But because negative 163 gives us a class number of exactly 1, it mathematically guarantees that we remain in a unique factorization domain. It means that even in this bizarre, highly complex geometric space, numbers still factor perfectly into primes without any ambiguity whatsoever.
And why is that lack of ambiguity so critical here?
Because it is the absolute bedrock requirement for the lossless data compression they achieve later on. If your factorization is ambiguous, you cannot perfectly reconstruct data from its constituent parts. You'd be guessing. The UFD guarantees you never, ever have to guess.
Wait, let me stop you there, because we need to bridge a massive conceptual gap. You're telling me that instead of tweaking the C++ memory allocation, they went into deep number theory, picked a very specific curve based on its unique factorization properties, and mapped the AI onto it.
Yes.
But how do you actually do that? I mean, an AI model is made of massive tables of weights, rows and columns of floating point decimals. It's basically an Excel spreadsheet of math. A curve is a geometric shape. How do they actually translate a spreadsheet of AI weights into a point on a curve in the first place?
That is the crucial missing link. You don't just paste an Excel spreadsheet onto a curve. Imagine a massive coordinate plane. Instead of treating the AI's data as isolated decimals in a table, the Shannon-Prime framework treats those rows and columns of numbers as the coefficients of a giant polynomial equation.
Okay, so the data becomes the formula itself.
Yes. They encode the dimensions of the AI into polynomial coefficients, and then they evaluate those polynomials over the specific mathematical field of our curve. The AI's data literally becomes coordinate points that live on the surface of this mathematical shape.
So they're essentially translating the language of data tables into the language of geometry.
Precisely. They map the state of the neural network onto the geometric topology of the curve, and once the AI is living on that curve, the rules of the curve govern the AI. Which brings us to how this unique factorization domain structure enables their variable hierarchical transform-to, or VHT2 process, which they use to compress the KV cache with absolutely zero loss of information.
Okay, let's get into VHT2. This is the mechanism for compressing the K, or the key, part of the KV cache. According to the systems paper, this involves 3 steps: spinal rotation, square-free indexing, and Mobius inversion. Let's take these one by one. Spinal rotation sounds like something straight out of quantum physics.
It has roots there, yeah. But in this context, the spinal rotation is largely an alignment step. Even though we are in this beautiful mathematical space, we still have to eventually run this on physical silicon chips. The spinal rotation rotates the mathematical basis of our data into a representation that is highly favored by the physical architecture of modern hardware accelerators.
Got it. So it aligns the geometry with the silicon. It's prepping the canvas. But the real heavy lifting happens with the next 2 steps. Governed by Theorem 2, in their theory paper, the Mobius UFD compression. How does Mobius compression actually compress anything?
Well, because we established that the curve operates in a unique factorization domain, we know every number, every coordinate factors perfectly into primes. This allows them to unleash something called the Mobius function. The Mobius function is a tool from number theory that essentially analyzes the prime factorization of numbers. What Theorem 2 rigorously proves is that they can store the AI's cache data only on the memory indices that are square-free.
Square-free. Let's define that.
Yeah.
A square-free number is a number that isn't divisible by any perfect square other than 1. So the number 10 is square-free because it's 2 times 5. No squares there.
Right.
But 12 is not square-free because it's divisible by 4, which is 2 squared, or 18, which is divisible by 9, which is 3 squared.
That's spot on. Now, if you look at the grand scheme of all integers, square-free numbers are actually surprisingly sparse. They make up only about 60.8% of the total integers.
So wait, are you saying they are entirely ignoring roughly 40% of the data indices? Like, they just choose not to store 40% of the AI's short-term memory?
They don't store them at all in physical memory. They literally leave those memory addresses empty.
Yeah.
Because of the UFD structure and the mathematical properties of the Mobius inversion formula, they can take the 60.8% of the data they did store on the square-free indices, run it through the Mobius function, and mathematically perfectly calculate what the missing 40% must have been on the fly.
Wow. Going back to a simpler analogy, it's like a massive game of Sudoku. If I give you a perfectly designed, partially filled Sudoku board, you don't need me to transmit the rest of the numbers to you over a network.
No, you don't.
Right. The fundamental rules of the grid itself dictate exactly what the missing numbers must be. The unique factorization domain is basically the infallible rulebook that lets them leave out 40% of the puzzle and rebuild it flawlessly.
That is a brilliant analogy. Yes, the structure dictates the missing information.
But play devil's advocate again. If I have to stop and solve the Sudoku puzzle every single time I want to recall a memory, doesn't that add massive compute time? If we compress 40% of the data using Mobius, aren't we just trading a memory bottleneck for a processing bottleneck? How is rebuilding data on the fly faster than just reading it?
It's a highly valid concern, but the math is stunningly efficient. The paper notes that for a typical vocabulary size in a large language model, reconstructing any missing vector using the Mobius inversion takes fewer than 5 multiplications.
Fewer than 5 multiplications. That's nothing.
It's computationally trivial for a modern GPU or NPU. It takes almost 0 time, but the amount of physical RAM it saves by leaving 40% of the cache empty is monumental.
Okay, so that handles the keys in the KV cache. What about the V, the values? Do they get the Sudoku treatment too?
For the values, they use a different geometric trick called a spinor reconstruction. Normally, a value vector in a transformer has a massive full dimension, let's say 4096 separate floating point elements just for one token. By leveraging the algebraic properties of how data maps onto this specific elliptic curve, they can project that entire 4096-dimensional row down to just 2 elements, a simple paired coordinate.
That is a staggering reduction. You're taking a row of 4096 numbers and compressing it down to just 2 numbers.
It is extreme compression. And to push it even further, for highly constrained edge environments, like running an AI on a smartwatch or a cheap IoT device, they introduce what they call a ternary skeleton. They split the key tensor into a basic skeletal structure that only takes values of -1, 0, +1, plus a tiny residual part to catch any overflow.
Okay, so we have spinor rotations, Mobius square-free Sudoku grids, dimensional projection, and ternary skeletons. What are the actual real-world results of combining all this complex machinery? Because, I mean, it's one thing to have a neat math theory. It's another to actually compile this and run it.
They did run it. The systems paper details their benchmarks. On the Mistral 7B model, which is a very popular, highly capable open source model using the ternary skeleton plus the split KV compression we just discussed, they achieved a 6.2x compression of the KV cache.
6.2 times smaller. So our 34 gigabyte nightmare from earlier just shrank down to about 5.5 gigabytes, which comfortably fits on a standard smartphone.
It does. But here's the most crucial part. The metric that should make every AI engineer listening sit up in their chair. They achieved that 6.2x compression with exactly 0 perplexity delta.
Let me stop you and repeat that for the listener, because 0 is a dangerous word in software engineering. Perplexity is the metric we use to measure if an AI is getting dumber or more confused, right?
Right.
A higher perplexity means the model is making worse predictions. When you say 0 delta, do you mean practically 0, like 0.0001% degradation, or do you mean literally mathematically 0?
I mean, literally mathematically 0. The model's output quality did not degrade by a single fraction of a percent. It is exactly as smart, exactly as accurate, exactly as coherent, but its memory footprint takes up over 6 times less physical space.
That violates almost everything we've understood about compression for the last decade. How is that possible?
Because it's not an approximation. They aren't throwing away socks. The UFD guarantees exact reconstruction. The Mobius inversion is mathematically lossless.
So what does this all mean for you, the listener? Let's extrapolate this into the real world. If you have a phone that currently struggles to run a small 3 billion parameter model because the cache fills up your RAM and crashes the app, a 6.2x exact compression means your current phone could suddenly run an 18 billion or maybe a 20 billion parameter model locally, completely private.
Yes.
With no cloud GPU required and without the model suddenly acting stupid because its memory was compressed.
And it's not just about memory capacity, it's about sheer speed. The Snapdragon 8 benchmark, detailed in the systems paper, shows this framework running a Qwen 3 billion parameter model on a standard Samsung phone CPU. Not the specialized neural engine, not the GPU, just the standard CPU.
Wow.
And it achieved a 3.58x speedup over the vanilla uncompressed baseline. It jumped from generating 12 tokens a second to almost 44 tokens a second.
44 tokens a second on a phone CPU is blistering. That's faster than the average human can read the text as it appears on the screen.
Okay.
So we've perfectly compressed the cache, we've solved the 34 GB wall, but the KV cache is only one part of the model. What about the model weights themselves?
The parameters, right?
Yeah, the actual billions of parameters that make up the AI's brain. Usually, to fit a model on a phone, we take those weights, we crush them from high-precision 16-bit floating point numbers down to 8-bit or even 4-bit formats. And doing that almost always damages the model, doesn't it?
It absolutely does. It is historically a very destructive process. And this brings us to Theorem 4 in the Shannon-Prime theory paper, Frobenius quantization. To understand why standard quantization damages models and why the Shannon-Prime method doesn't, we have to look at the mechanical reality of what happens when you quantize a number.
Let's unpack this. What actually happens when an engineer quantizes a model today?
In traditional quantization, you are taking a high-precision floating point number, say a 16-bit float, which has a lot of decimal places of accuracy, and you are literally chopping off those decimal places to cram it into an 8-bit space. You are rounding the numbers.
Right.
The problem is you are treating the data as raw, disconnected numbers. But a trained neural network isn't just a pile of numbers. It is a massive, delicate web of multiplicative relations.
Okay, so they rely on each other.
Exactly.
Yeah.
The model learned during training that weight A times weight B directly relates to activation C. When you round weight A and weight B individually, you shift them just enough that the delicate algebraic relationship between them is broken.
You're introducing variance. It's like taking a finely tuned Swiss watch and taking a metal file to all the gears so they fit in a smaller case. The gears might still fit, but they don't mesh perfectly anymore. The watch loses time. We call it giving the model brain damage.
That is exactly what happens. And to fix that brain damage, the industry relies heavily on something called calibration data. They take the damaged 8-bit model and they run thousands of samples of training data through it to see how badly they broke the predictions. Then they painstakingly calculate scale factors and mathematical offsets to try and push the broken, rounded math back into roughly the right shape.
Which is an absolute pain. It requires curating a perfect data set. It requires massive compute time just to run the calibration. And honestly, it's never perfect. The model never fully recovers.
No, it doesn't.
But the Shannon-Prime framework claims they don't need calibration data at all. They claim calibration-free quantization. How is that even mathematically possible?
This is where the magic of mapping the AI onto the CM elliptic curve pays off yet again. Because the entire state of the model is now mathematically encoded as geometric points on this specific curve, reducing the precision, say moving from a 16-bit representation to an 8-bit representation, is no longer a crude act of rounding off decimals.
Okay, so what is it?
Instead, they apply a geometric transformation called the Frobenius endomorphism.
The Frobenius endomorphism. Okay, we've got another heavy term here. What is an endomorphism, and what does the Frobenius version of it actually do?
In simple terms, an endomorphism is just a mathematical transformation that takes a shape and maps it back onto itself perfectly, preserving all its internal structure. You aren't warping the AI's data into a new messy shape, you're just folding it perfectly along its own seams.
Oh, I see.
Specifically, the Frobenius endomorphism maps every coordinate on our curve to its p-th power, where p is a specific prime number we choose.
Yeah, okay, so it maps the data to a power of a prime. But how does that shrink the data without breaking the Swiss watch?
Here is the critical property, and this is the absolute core of Theorem 4. On a complex multiplication curve, the Frobenius endomorphism commutes with all other layer operations in the neural network.
Commutes. Like in basic algebra, A times B equals B times A. The order doesn't matter.
Yes. Think about the implications of that. Matrix multiplication in neural networks usually does not commute. The order matters immensely. But because the Frobenius reduction commutes with the model's fundamental operations, it preserves every single algebraic relation in the model exactly. The structural web of the model, the way the gears in the watch mesh together, is maintained by mathematical definition.
So you aren't breaking it.
Exactly. You aren't breaking the math and trying to tape it back together with offsets. You are translating the math flawlessly into a mathematically smaller space. It's like projecting a 3D shadow onto a 2D wall. The shadow takes up less space, but the angles and proportions of the original object strictly dictate the shadow's shape.
That makes a lot of sense. So because the structure is perfectly preserved by the geometry of the endomorphism, zero calibration data is required to fix it, because there's nothing to fix.
None. The structure is mathematically protected. The systems paper states this retroactively explains why their FP8 quantization succeeds effortlessly, where standard FP16 to FP8 rounding fails catastrophically. They are implementing a Frobenius projection, not a rounding error.
That is a fundamental paradigm shift. It means you decouple the act of quantization from training data entirely. This unlocks the potential for deploying FP8, and they even mention FP4 or FP10 models with literally zero training or calibration overhead.
Zero overhead.
You don't need a supercomputer to shrink your model anymore. You just mathematically step down the precision using the curve, and the model remains perfectly intact.
It democratizes model deployment in a way we haven't seen before.
But I have to play the skeptic again. This sounds almost too good to be true. Like, We found a magic math trick that requires zero calibration and perfectly preserves the model.
Mm.
If I'm an engineer listening to this, I'm thinking, why isn't everyone doing this right now? Is there a catch when you actually try to run this on silicon?
Naturally.
Right. It's one thing to prove a beautiful theorem on a chalkboard. It is an entirely different beast to run it on a GPU and get good text generation.
That is exactly the right question to ask, and the Shannon-Prime team anticipated that exact skepticism from the engineering community. They knew software engineers would demand hard, undeniable proof, so they designed a highly specific, high-stakes experiment to validate the theory in the real world, which is detailed in the companion systems paper D. And it relies on choosing a very special prime number for that Frobenius power we talked about.
Let's dive into this gauntlet they set up. They use the Phi-3 model as their test subject, right?
Yeah.
Why Phi-3?
A few practical reasons. First, Phi-3 is their heavily calibrated reference model, meaning the researchers already know exactly how it behaves under standard non-Shannon-Prime conditions.
As a known quantity.
Exactly. Second, it's relatively small, about 3.8 billion parameters, which means it fits easily entirely on a single A100 GPU. That allows them to run benchmarks very quickly without multi-GPU communication bottlenecks. And finally, it has a very clean architecture. It doesn't have some of the bizarre architectural quirks that complicate other open source models. It's the perfect clean room for a math experiment.
So they take Phi-3 and they apply this calibration-free Frobenius quantization using a specific prime number. And there's actually a really interesting footnote in the source material here regarding this prime. In an earlier draft of the paper, version 02, they thought that prime number 11 was the right choice for the endomorphism.
Yes.
But their test suite caught an anomaly, a mathematical error, and in version 0.3, they corrected it to prime 41. What makes the number 41 the magic bullet here?
This gets into the deep geometry of our specific sandbox, the curve Q root negative 163. The prime numbers behave very differently in this complex space compared to normal integers. In this field, 41 is what is known as the smallest split prime.
Smallest split prime. Let's translate that. What does a split prime do functionally to an AI model?
Functionally, it relates to the error margin. Remember when we talked about the Frobenius endomorphism being like a shadow? Well, depending on the prime you use, that shadow can be slightly blurry. This blurriness is governed by something called its Sato-Tate angle.
The Sato-Tate angle.
Yes.
Yeah.
Think of the Sato-Tate angle as the mathematical variance or analytic drift that is naturally introduced when you apply the Frobenius endomorphism. It is a tiny inherent vibration in the math.
I see.
Because 41 is the smallest split prime in this specific field, it gives a Frobenius drift that is bounded by a mathematical absolute value of exactly 1. That is the smallest possible non-zero drift for any split prime on this entire curve. It's essentially the tightest, cleanest, mathematically bounded reduction you can physically perform.
So by choosing 41 instead of 11 or 73 or whatever, they are deliberately minimizing any inherent mathematical noise in the system to the absolute theoretical limit of the curve.
Exactly. It's not a random guess. It is mathematically provably optimal for this specific geometric space.
Okay, so they have their optimal prime, 41. They have their clean room test bed, Phi-3. How did they structure the actual experiment to prove to the skeptical AI community that this calibration-free theory actually works?
They set up a comparison gauntlet across 5 distinct configurations to isolate the effect. Let's look at the baseline first. Config A is the baseline. Just standard, full precision, FP16 Phi-3, no compression, no tricks. This is the ground truth of how smart the model is.
Right, and then they need to test their blind newcomer.
Yes, config B is the Shannon-Prime FT8 model. This is their pure mathematical method using prime 41 with absolutely zero calibration data. It has never seen a single piece of training text to correct its weights. This is the primary hypothesis being tested.
And to prove it's actually useful, they have to compare it to the reigning industry champions, the methods everyone uses today.
That's where config C and config D come in. Config C is GPTQ, which is arguably the leading industry standard algorithm for FP8 quantization right now. And GPTQ requires a curated set of about 1,000 samples of calibration data to fix the rounding errors.
Okay, so C is GPTQ.
Right. And config D is AWQ, another top-tier industry standard, which also heavily relies on 1,000 calibration samples.
And there's a config E, but we'll hold off on that for a second because it introduces a whole new wrinkle.
Yeah.
Let's look at the criteria for this gauntlet. For Shannon-Prime to claim victory, the criteria are incredibly steep. Config B, their totally uncalibrated, mathematically derived method, must match the pristine baseline config A within a tiny 0.5% margin of error on perplexity.
Right.
It has to be virtually indistinguishable from the massive uncompressed model. And furthermore, it has to match the heavily calibrated industry standards, GBTQ and ADWQ, within a 0.3% margin.
They are throwing down the gauntlet. They are claiming they can match or beat the best, most heavily calibrated, painstakingly engineered quantization methods in the world without looking at a single piece of training data.
To bring back an analogy, it's like showing up to the finale of a world-class baking competition, right? And you refuse to taste your batter even once. You do zero calibration.
Yeah.
Meanwhile, the industry pros GPTQ and AWQ have been taste testing and adjusting their recipes 1,000 times in the kitchen.
Exactly.
And you still tie them for first place simply because your underlying chemical recipe is mathematically perfect.
It is an incredibly bold claim, and the experiment is designed to be highly falsifiable. If config B's perplexity degrades beyond that 6.5% threshold, the entire theory is dead in the water. It means the Frobenius endomorphism wouldn't be preserving the structure as claimed.
It's a massive high-stakes test. But let's bring in config E now. Config B tests a single prime 41, for a standard 8-bit format. But AI deployment is getting greedy. We don't just want flat 8-bit or 4-bit models anymore. The industry is aggressively moving towards mixed precisions, like FP10 formats.
Yeah, that's where things are heading.
Where some critical parts of the neural network are stored at higher precision than other, less important parts.
Yeah.
How do you mix precisions using this math? If you use different primes for different parts of the model to get different bit widths, don't you ruin that elegant commutativity we just talked about? Don't you tear the fabric of the curve?
That is a phenomenal question, and it is exactly what Theorem 3 in the paper addresses. Theorem 3 introduces the concept of the Sato-Tate asymmetric mixed precision quantization.
The Sato-Tate distribution. You mentioned the Sato-Tate angle earlier regarding the drift, but let's really dive into the mechanics of this. How does a mathematical distribution allow for mixed precision AI models?
It relies on a beautiful fundamental property of how prime numbers behave under this specific CM curve. Under the CM Sato-Tate distribution, the prime numbers are perfectly partitioned into two distinct camps. Exactly half the primes are what mathematicians call inert, and exactly half are what we discussed earlier, split.
Okay, inert and split. Let's define the difference mechanically. Let's start with the inert primes.
An inert prime, and the paper uses the prime number 2 as their primary foundational example here, so P1 equals 2, has a deterministic, mathematically guaranteed Frobenius trace of exactly 0.
0. As in absolutely zero variance, zero drift.
Precisely 0. If you build a quantization channel using an inert prime like 2, it has provably 0 quantization drift. It is completely mathematically stable, it does not vibrate, there is no variance whatsoever.
And the split primes, like our friend prime 41.
Split primes, like 41, have a bounded analytic drift. As we discussed, for 41, that drift is bounded very tightly by an absolute value of 1, but it is fundamentally non-zero. It has a slight variance.
So let me visualize this if I'm understanding this correctly. Config E from the experiment takes these two fundamentally different types of primes and physically combines them to create a new format.
Yes. Config E combines 2 bits of precision derived from the inert zero drift channel using prime 2, and it literally staples that together with 8 bits of precision from the bounded drift split channel using prime 41.
Stapling bit widths together. How does the math not collapse?
Mathematically speaking, it creates a composite quantization. They apply the Frobenius reduction for prime 2 to handle the highest stakes data, and then they apply the Frobenius reduction for prime 41 for the rest. Because we are still operating in that commutative space on the elliptic curve, the order of operations doesn't matter.
It still commutes.
Exactly. The two channels blend together perfectly without breaking the underlying algebra.
So we end up with an FP10 format. 2 bits of rock-solid inert precision and 8 bits of bounded split precision. But why did they include this in the gauntlet? Why does config E provide a sharper, more rigorous test for the zero drift theory than config B did? Config B was already a huge risk.
This raises a vital point about experimental design and the scientific method. Config B just proves that the Frobenius endomorphism works generally for a single split prime. It proves the shadow works. But config E tests the deep partition theory of the Sato-Tate distribution itself. It tests whether the inert prime truly acts as a perfect mathematical anchor.
Oh, I see where this is going.
Think about the stakes. If config B, the 8-bit single prime, works perfectly, but config E fails, it means their prediction about the inert channel having 0 drift is fundamentally wrong.
Ah, because if the 2-bit inert channel had any drift, adding it to the 8-bit channel would compound the errors, and the perplexity would spike. If E fails, it means the inert prime wasn't actually anchoring anything. It was just introducing noise instead of stability.
That's the crux of it. It is a highly falsifiable test of the entire geometric framework. By combining them, the researchers are saying, we believe in this abstract math so deeply, we will add a 2-bit inert channel to an 8-bit split channel, and we predict the total error of the combined FP10 model will be identical to the 8-bit channel alone, because the 2-bit channel mathematically adds 0 drift.
It's like building a boat. The inert prime is this massive, heavy lead keel at the bottom of the boat. It mathematically prevents the boat from capsizing. It provides 0 drift. And because you have that massive anchor, you can build a massive complex 8-bit mask, the split prime on top of it, without the whole thing drifting into chaos. Is this what eliminates the variance we usually see when engineers try to build mixed precision models today?
That is exactly the claim. Standard mixed precision schemes today, where engineers might arbitrarily decide, the neural network weights are 4-bit, but the activations are 8-bit, they require massive empirical calibration. Because when you mix those precisions, the rounding errors compound chaotically and have massive, non-trivial variance. The Sato-Tate mixed precision has 0 variance on the inert channel and a bounded predictable variance on the split channel. It is variance-free without looking at a single drop of calibration data.
It is just mind-blowing. It changes the entire paradigm of AI engineering from measure the error and write software to fix it to design a geometric system where the error is mathematically bounded by definition so it never happens in the first place.
It's the difference between treating the symptom and curing the disease.
So let's look at the bigger picture. Once you prove that the geometry of elliptic curves solves the memory crisis with exact Mobius KV cache compression, and once you prove it solves the precision crisis with calibration-free Frobenius and Sato-Tate primes, completely abandoning lossy heuristics, you have to ask the natural next question.
What else can we fix?
Exactly. What other messy, computationally expensive parts of the modern transformer architecture can this math clean up? What else can we replace with geometry?
And that leads us beautifully to the final section of the theory paper, which explores future horizons and adjacent extensions. Because once you've done the hard work of translating the model so it lives on this curve, other notoriously complex operations naturally simplify.
What's a good example of that? Because right now, under the hood, transformers are a mess. They have all these random normalization layers stacked everywhere just to keep the numbers from spiraling out of control.
That is the perfect example. Currently, transformers heavily rely on layer normalization algorithms like RMS norm. As data passes through the dozens of layers in a deep neural network, the residual stream, the core pathway of data, tends to explode.
Oh, right.
If you don't aggressively normalize the data at every single layer, the numbers get too big, they grow exponentially, the gradients vanish, and the model essentially collapses into gibberish.
It's like audio feedback on a microphone. If the microphone is too close to the speaker, the sound loops, multiplies, and if you don't have an engineer actively suppressing it at the mixing board, it deafens everyone in the room. RMS norm is the engineer writing the volume fader at every single layer.
Exactly. It requires constant compute power to calculate those normalizations. But the Shannon-Prime project proposes something entirely different called Iwasawa Tower depth scaling.
Okay, Iwasawa Tower. That is a new one. Let's unpack the mechanics of that.
Instead of viewing the transformer as a flat, sequential stack of layers like pancakes, they view the entire stack of layers algebraically as a mathematical structure called a Z-extension tower drawn from Iwasawa theory. By treating the layers this way, the math allows them to algebraically enforce a property called the mu equals 0 invariant.
And what does enforcing the mu equals 0 invariant actually accomplish physically within the model?
It acts as an unbreakable algebraic constraint on the data as it moves between layers. If you mathematically enforce mu equals 0, the growth of the residual stream is strictly bounded linearly rather than exponentially. The p-adic valuation of the numbers simply cannot explode.
So the audio feedback loop is physically broken by the fundamental math of the space. You don't need the engineer writing the volume fader because the laws of physics in this space prevent the volume from exceeding a certain level.
That's the reality of it. What this means practically for deployment is staggering. You could theoretically build a 1,000-layer reasoning model, a truly massive, incredibly deep, highly intelligent transformer with 0-layer normalization overhead.
None.
No RMS norm required anywhere in the entire 1,000-layer stack.
That is huge. Calculating RMS norm at every single layer for billions of parameters takes a massive amount of matrix multiplication, stripping that computational burden out entirely while simultaneously allowing the model to be 1,000 layers deep. That changes the scale of the intelligence we can run on edge devices. What else in the architecture can they rip out and replace?
They also target the core of the transformer itself, the attention mechanism. Standard models use something called scaled dot product attention, which is usually combined with a softmax function to determine which words the AI should focus on. It works, it's why ChatGPT exists, but it's computationally heavy and mathematically clunky.
Yeah, we spend so much compute on attention.
Right. The Shannon-Prime paper proposes replacing that entire multi-step attention mechanism with a single, elegant, bilinear operation on the elliptic curve called the Weil pairing.
The Weil pairing attention, how does that work?
In the paper, it's denoted as NQK. Instead of multiplying matrices, scaling them down, and running them through an exponential softmax function, the Weil pairing computes the attention mathematically in a single unified step. It leverages the inherent pre-existing geometry of the curve to directly determine the relationship and the distance between the query token and the key token.
It really feels like these pure mathematicians are looking at the current state-of-the-art AI transformer architecture and saying, you guys built a really cool, really functional house out of duct tape, cardboard, and heuristics. It works, but we can just cast the whole thing in a single, unbreakable block of solid concrete.
That's a very apt way to look at the cultural divide here. If we summarize the main benefits of these methods for students, researchers, or anyone learning about transformer acceleration, it represents a massive paradigm shift in how we approach the field.
If you are listening to this and you're studying AI, or you're an engineer trying to implement local models, the main takeaway from the Shannon-Prime project is the philosophical shift from empirical heuristics to mathematical guarantees.
Absolutely.
You no longer have to guess if a new compression technique is going to be lossy. You don't have to blindly tune calibration datasets and hope you didn't accidentally lobotomize your model's ability to code or speak French. The math provides the absolute boundaries.
The theory paper makes a point to explicitly state that the Hasse-Weil bound, which is a theorem that governs the absolute maximum number of points that can exist on these elliptic curves, actually acts as the definitive Shannon limit for the AI model's information capacity. It tells you, with mathematical certainty, exactly how much data a layer can hold. No more, no less.
Which highlights a fundamental difference in philosophy between software engineering and pure math.
It does. Engineering, especially in cutting-edge software and AI, usually relies heavily on trial, error, and iteration. You build a model, you test it, you see it hallucinate, you tweak the weights, you test it again.
Right, it's iterative hacking.
But Shannon-Prime relies on the absolute, unyielding, eternal laws of number theory. It's the difference between building a bridge by guessing how much steel you need based on the last bridge you built versus calculating the exact atomic physics of the load limit before you pour a single ounce of concrete.
So let's take a step back and summarize the incredible journey we've been on in this deep dive. We started with a massive, practically insurmountable 34-gigabyte memory bottleneck, the KV cache, that was crushing our ability to run models locally on phones.
And we saw how the Shannon-Prime framework bypassed that, not with better hardware, but by translating the entire transformer architecture onto an imaginary quadratic field, specifically the Heegner number Q root -163.
Because that specific, intimidating number gave us a mathematical sandbox with a class number of 1, creating a unique factorization domain. And that UFD allowed them to use the Mobius function and square-free indexing to perfectly compress the KV cache by over 6 times without losing a single drop of accuracy.
The origami suitcase folded flat.
The origami suitcase. Then they tackled the AI's actual brain the model weights. Instead of lossy rounding that causes brain damage and requires thousands of samples of calibration data to fix, they applied the geometric Frobenius endomorphism.
And because that geometric projection commutes with all the layer operations, they achieved exact FTA quantization without looking at a single piece of calibration data.
And when they needed advanced mixed precision, they leveraged the Sato Tate distribution, partitioning prime numbers into inert and split categories. They combined the zero-drift inert prime 2, which acted as a mathematical anchor, with the tightly bounded split prime 41, creating a calibration-free, variance-free FP10 format.
It is a complete mathematically grounded, rigorous overhaul of the entire AI inference pipeline.
It's elegant. It's not duct tape, it's pure geometry. But before we sign off, there is one final deeply provocative thought hidden at the very end of the theory paper that we haven't touched on yet. And it has to do with something way beyond compression. It has to do with how an AI actually learns and remembers things over the long term.
Ah, yes. Section 10, the implications for catastrophic forgetting.
Right. Anyone who is trying to fine-tune an AI model, or even just used one extensively, knows about catastrophic forgetting. You take a smart model, you teach it a brand new skill, say you spend hours fine-tuning it to write code in Python, and suddenly you realize it has completely forgotten how to speak French or solve basic logic puzzles.
Right. The new data literally overwrites the old data in the floating point weights. It's a massive, unsolved problem for creating an artificial general intelligence that can continuously learn over its entire lifetime without wiping its own memory.
It's an inherent flaw in how we store data in flat matrices. But under the Shannon-Prime framework, because the model lives on a curve, the training objective changes entirely. Instead of trying to minimize cross-entropy over a continuous, easily overwritten floating point space, the paper suggests a radical new training method, maximizing the analytic rank of the curve's L function.
Maximizing the analytic rank of an L function. We are ending on some heavy math. This is based on the Birch-Swinnerton-Dyer conjecture, isn't it?
The BSD conjecture, exactly, which for the listener is literally one of the Millennium Prize problems. It's one of the greatest unsolved problems in mathematics, and they are applying it to AI memory.
They are. The core idea is this. If you train the AI by maximizing that analytic rank, the model's long-term memories are no longer stored as fragile, easily overwritten decimal values. Instead, they are encoded as generator points within what is called the Mordell-Weil group of the curve.
Meaning the memories become combinatorial structures, not analog values that can be nudged or erased.
Yes. And because they are fundamental geometric points on the curve itself, they are topologically protected. You can reduce the precision locally, you can quantize the model, you can change the working prime to run it on a smaller device, and those foundational memories cannot be overwritten or mathematically erased. They become permanent, structural, load-bearing features of the curve the model has learned.
Think about the implications of that. This means an AI could continuously learn new things, adapting to new environments for years without ever overriding its foundational memories or its core instructions. It solves catastrophic forgetting not with a clever software trick, but through the fundamental topology of mathematics. It's something for you to mull over as you think about the future of a truly lifelong learning AI. The diagnostic muddy waters of lossy heuristics are finally clearing up, and the mathematical precision we are moving towards is absolute. Thank you for joining us on this deep dive into the source material.